All right, so welcome. I need to use the mic because so the Zoom can get my audio. So anyway, welcome back. I think today is a great day that we move to a new environment. But anyway, I have just one announcement and then I can proceed to the class. Today we have two lectures, distillation and also parameter efficient tuning. So the first announcement is 99% already confirmed that I will be traveling to China to promote data science program from 7 March to 20 March. So that is like 13 days, right? So there will be a lot of classes that we miss, but I calculated we only missed 2 classes because one of the classes quiz, another class is he will teach anyway, right? So we will miss 2 classes. What I will do is I will record video and then you guys go watch, okay? So that would be the plan, yep. But anyway, I will make sure that me on the YouTube is the same experience as me here, okay? But anyway, let us go to distillation. Right, so knowledge distillation is a very powerful technique introduced in the year 2014. And you may think that this is a very old idea, right? But the first motivation is that the model can be very big. Can we make it smaller? And the answer is, if we want to make it smaller, we need to think about compression techniques. And knowledge distillation, or we call model distillation, is a very, probably the most successful technique. So for compression technique, there are many techniques, and I can write it down here. There is knowledge distillation. All right, so this is the first compression technique. Second one is pruning. And the third one is quantization. Right, so they are all to make sure that we have small models. At the same time, today, because we are already talking about efficiency, we will also talk about a so basically, usually we talk about fine tuning, right? But the question is, how do we fine tune in such a way that is very cheap? And that is called parameter efficient. Actually, it's not parameter efficient fine tuning, I think, but probably is correct, right? I think that is the idea. So this is like how to fine tune efficiently. Efficiently means using local GPU. So today's topic is like so important for all of you, especially if you're working in industry. So distillation, if you understand today, this slide is finished already, right? So the idea is very simple. Imagine that you have Chucky 8 hamburgers and mass. You send to the bird 12 layers transformer, and we call this a teacher. So you need to understand the term called teacher. Teacher is the name to represent the original model. The original model that contains all the knowledge. And then you get a distribution. So the distribution that fries is 50%, Coke 20%, cheese 5%, right? I initialize. So this one is a pre-trained model. The bird is a pre-trained model, but we create a 6-layer transformer, initialize it randomly. By the way, whether we initialize randomly or we copy some part of that, it doesn't matter. But what is matter is we got a 6 layer, like much smaller than this, right? This one can be 3 layer, 4 layer, 8 layer, any layer that is smaller than this, understood? It can be, the idea is that we want to create a much smaller model than this one. How small, it doesn't matter. You can make 6, you can make 8, 12. How to initialize also does not matter, because you can initialize randomly or you can copy some layer and put it here, okay? These are all contained in the techniques of distillation. And you call this guy student. And here, because I call this a student, I just don't want to change. I don't want to call this bird, so I just say I call this Distil bird, okay? But actually, this is just a randomly initialized 6-layer transformer, let's say, okay? Then what I do is I send the same input, right? And this guy also predicts something, right? Correct? This guy also predicts something, right? Then what I do is that I take 2 of this thing. You got this one, right? And this one. You take 2 of this thing and cross entropy loss. All right? By cross entropy loss between these 2, right? You allow the student to learn from the teacher. This is the key idea, right? This is the key idea. And one thing you may wonder, like, why you don't let this guy predict something and let this guy predict the best one, like the fries, and just cross entropy? Well, what we found is that in distillation, if we distill the distribution, not only the specific target, the student can actually learn better like the distribution, right? So basically what I'm trying to say is that distillation learns better through distribution, not the answer, not the specific answer. You got my point, right? So for example, if I argmax this one is fries, right? And maybe I would just say, this guy, please try to answer like your teacher, okay? Fries. But that one is not effective because it's much better for your student to learn not only the highest probability, but also the distribution, right? That would allow your student to learn more information from your teacher, right? So this is the key point of distillation. And if you understand this slide, you probably already understand everything about distillation, because distillation only have this way, right? But this is like the core concept of distillation. That is, you create a much smaller model, and then you create a teacher, and then you just let the smaller model learn from the distribution that the teacher gives you, right? So this is an extremely powerful technique. Anyone has any questions? Yes. I really want you all to make sure you understand this. If anyone work in NLP in industry or gonna come to my lab to do research, I'm very sure you will come across this technique. I'm very sure. Anyone has any question? Cool. Okay. Cool. Okay. Great. So, in fact, what I just showed you is called Distil bird, that is presented by San in New Lips 2019. For those who don't know New Lips, if you just get 1 or 2 New Lips, you already can go to study at MIT PhD program, for example. So New Lip is a very good conference, just like ACL, right? Just like ACL. But anyway, my point is that you may wonder, a 6-layer and a 12-layer, which one is better? Probably the 12-layer, right? Probably the teacher. But this guy say that I cut half of the layers, but it can retain 97% performance, right? That is like so amazing. You cut half of the layers, but it can get 97. It can retain 97% of the teacher, right? This is like so cool, correct? You cut half of the layers. When you cut half of the layers, the inference speed increased by double, right? Increase double, but you lose only 3% performance. Are you willing to do it? You are for sure doing it, right? Because if I use ChatGPT, I want my user to get the response very fast, right? If I can make it faster 2 times, but the accuracy of the response just lose 3%, I will definitely do it, right? So you can see that Distil bird is super nice, right? Now, they also do something called ablation study. What is ablation study? Ablation study is basically they try to take some components out and try to see which loss is important, right? So I want you to take a look very closely, right? So this mark, this null sign represent the distillation loss. All right. So this distillation loss is nothing. That is when you predict, you should predict same like a teacher. Okay. So this is the distillation loss. The number 2 is the by the way, this is not minus. Okay. This is mean they don't have this, they don't have this, they don't have this. Okay. This is not minus. This loss is the cosine embedding loss between the hidden state vectors, between the teacher and the student. So for example, I'm so sorry for the flexible students, but you can listen to me while I'm writing on the whiteboard. So for example, you have a bird and there's a 12 layers, right? Right, and you have teacher, and you also have 6 layers, and this is 12 layers, right? Correct. The first loss is that once you pass in the input, you get the y, right? You pass in x, and let's say you call this y2 and y1, right? The first loss, which is this one, is basically the cross entropy between y1 and y2, right? Correct? So this is the first loss. The second loss, they call this cosine similarities, is simply as this cosine similarities is basically equal to, so there are 6 layers. I'm not sure how they exactly do, but this is like the simple idea. For example, maybe at the layer 6, you will have a hidden, you will have an H, right? That comes out from the layer 6. From layer 12, you also have an H, correct? Right? So let's call this H2 and H1. What you can do is you can do cosine similarities between H1 and H2, right? So this is the second loss they do. By the way, this can be done very creatively. By the way, does this block you? I don't know. I don't know. Can I move? Better? And the plug is gone. No, I don't think I can move as much as we want. Okay. Is it back or did I make it worse? Okay, anyway, I think you guys can focus on that. So here on the hidden vectors, you can do many interesting things, right? For example, this is the layer 5. You can take the layer 5 too. Let's call this H25. And you can take the layer 11 and you call this H111. And then you can also do H25 and H1. So basically, what you are trying to do is you try not only to mimic the teacher only on the target, but you also want to mimic the teacher on the hidden state vectors. You understand? Like not only the target, but also the inside vectors, right? The more you can be same, the better. But there will be a question. You may thinking already. Which vector to compare with which, right? They are 6 here, they are 12 here, they are not the same, right? You don't know 6 compare with who, right? This is a question that paper need to tell you. Different distillation have different way to map. Like some paper just say 6 map to 12, 5 map to 10, 4 map to 8, something like this. You understand? So this is one way you can do. Do you understand? Okay, good. Okay. I always stop first. Anyone has any question? Not there.
The distillation one, you said that they are not they are not just mapping the last one, but the
Exactly. So let me rephrase what I say. The first thing you mimic the teacher is this part, right? The target, right? But mimicking the target is not enough, right? What we found is that maybe you can mimic also the hidden state vectors, right? Right? And so what I can say is that maybe you can mimic H1 of the layer 12 and H2 of layer 6, right? Of the teacher and student, right? And then say that if they are very similar, I'm very happy, okay? So that is like one way. But I also want to creatively tell you that you don't need to restrict yourself to the last layer. You can do all the layers, right? But then I saw the Russia face. I can imagine her question that, then which layer map to which layer of the teacher map to which layer of the student, right? There's no theory, okay? So every paper has different way. That is something you have to do in your thesis. To learn how many ways are there, okay? So that is that. Lastly, they say they also have mass language loss, right? So what does this mean? So this is very simple. So this is my teacher, right? This is my teacher, 6 layer. I have Y2, right? This is the predicted mass token, right? So what I can do is first I argmax Y2, right? Consider this is a distribution. I take the highest probability. It's a word, right? Then I just simply do compare with the real, like the real Y, right? Like let's say the real Y of that mass token is like, I'm not sure, like I don't know. Let's say if my question is like Chucky is like this and this is the mass. If the input is like this, then maybe you compare with this, right? Right? And then you cross entropy loss. And this is the last loss they have, MLM. Okay? So all these 3 loss plus together. These are what this paper do. Okay? So hopefully I explain very clearly how this can be done. In coding, you may say how to code. Very, very easy. There's one tutorial that Gan has made is called Distil. He already showed you how to code this 3 loss in only 3 or 4 lines of code, right? So this is a very, very easy to do. So that's why it's a very good. Now, I want to, actually, I only have 20 more minutes. Actually, now you may ask me, which loss is the most important? I want you guys to think. Which loss is the most important? We don't know, right? But let you guys guess. Who say distillation loss? Okay, great. No one correct, no one wrong. Actually, I also don't know. We need to look at the results. Who think is the cosine similarities between hidden state vectors? Okay. Who say is the cross entropy loss, like the final loss of the student? Okay, great. And the rest is you want to know the answer right away, right? So, so this is why every NLP and computer vision papers have ablation study, like almost every papers, because ablation study can answer this kind of question, like which component is important. So if you delete everything, the loss is, I think is worse. Minus mean worse, okay? Your score reduced by 2.96. If you, okay, the second one is, okay. This one is the distillation loss. When you don't have, okay, I'm sorry, I think I named this incorrectly. This one, they call the distillation loss LCE, okay? This is what they call. So in the first one, when they take out the distillation loss, when the distillation loss is not here, the score is minus 2.96. When the cosine similarity is gone, the score minus 1.46. When the mass language modeling gone, the score is minus 0.31. If everything gone, minus 3.69. So in conclusion, which one is the most important? Distillation loss, all right? And number 2 is cosine similarities. Number 3 is mass language modeling. But if you combine all of them, it's the best, right? If you combine all of them, you can get 3.69 score up, okay? So you guys please remember this paper, because this paper is like original guy who do all this, right? So I think it's fantastic. How many minutes I have left before I could give to you? 2 minutes? Oh, 20, okay. I will not talk too much about this, but this is just another paper that is try to compare teacher and something called, okay, teacher, you guys understand, right? Teacher is the teacher. You guys understand pre-training and fine-tuning, right? You pre-train and fine-tune. Distillation is basically you don't do any pre-training, you just distill like what we do here. Basic training is like, you just forget about basic training. Basic training is like no pre-training, no fine-tuning, just like you just forget about basic training. But we also can do pre-train distillation. That is before you distillation, you pre-train your model first. That is before you distill, you pre-train your initialized model, right? Do you guys understand, or let me draw a little bit? Who don't understand pre-train distillation? Okay, let me just quickly draw. So pre-train distillation is simply like this, right? First, you initialize maybe an X layer of bird, maybe let's say bird, okay? A model. And this can be 6, this can be bird, okay? Right? If you just jump to distillation, if you just do distillation, it's called orange distillation. But what you can do is pre-train first. Pre-train first. And then distillation. All right? Distillation with who? With the 12-layer guy. With the 12-layer guys. All right, understood? This is called pre-trained distillation. So you create the model, but you pre-train it first before you distill. So which one you think better? Pre-trained distillation or distillation? Which one is better? Definitely pre-trained, right? Because you pre-train it first before you distill, so it's much better. And that is exactly what I find, right? And it's so surprising. The pre-trained distillation is the green dots. You see? The green dots. The green dots is even better than pre-training plus fine-tuning. Even better than. Like, so it is so surprising, right? Very surprising results that you don't need to do any full fine-tuning. You just do distillation and you can get the like almost equal to the teacher, sometimes even better than the teacher. The dotted line here is the teacher. Okay, this 4 box is different NLP tasks. So that is the idea. Anyone has any questions? Yep. Pretty cool, right? I think. This one is proposed in EMNLP. EMNLP is another very famous conference. If you have like many EMP, you can also go to MIT. It's called Tiny Bird. So you may wonder like, what is Tiny Bird? So now I can just delete this and quickly tell you what is Tiny Bird. Tiny Bird is simply, so let's say this is Tiny Bird. Right? Tiny Bird, you also initialize a layer, you pretain first, you distillation with 12 layers, right? But then you also do task-specific distillation. Task-specific distillation. So you also do task-specific distillation. With who? With who? Well, it can be with this 12-layer guys again, or it can be any guy that is very good in this task, okay? So this is Tiny Bird, that's it. So you can see that all the technique actually look the same, just that add a little bit one more, then they can publish the paper. And this paper also have, you may be like, Chucky, why they have so many laws? Actually, it's the same. The loss in the embedding. All right. So here embed, if I'm not wrong, is the first layer. Okay, like the embedding that go in, and you get the embedding. They make sure that they also have this kind of loss between the teacher and the student, and they also have a loss of the hidden vectors, just like that paper. But they also have loss between the attention state vector. You remember, if you do QKV, you will get a sequence length, right? You also do cosine similarity between this guy and the teacher. Also do this. They also do this. Yep. And of course, finally, they do the prediction, like basically the mass language modeling or whatever. That one is this one. So not everything the same, just attention. They also make sure that the attention of the teacher and the attention of the student look very similar. But you may have question. The student have 6 layers, the teacher have 12 layers. Which layer map to which layer, right? Again, this is something people need to experiment, okay? So that is the idea. Anyone has any question on this paper? Yes. So from this paper, it's very clear that, so Tiny Bird is right here, right? And Distil bird is right here. You can see that Tiny Bird, the main difference is the attention, right? Attention. The attention can make Tiny Bird better than Distil bird, right? So that is like a very interesting insights, but not by a lot, right? Like 91.4 to 92.6, like that's 1.2, but okay, it's better. We are crazy about little difference, but yeah, that makes a lot of difference. Now, you may wonder which one is the most important, okay? The embedding loss between the teacher and student, the prediction loss of the student, the attention vectors, or the hidden vectors. You don't need to remember TIM. TIM is basically the loss between vectors, okay? TIM is just a category of these two, okay? So how do we check? Oh, you can check that the score, the full score is 75.6, right? If you take out the embedding, is 74.1. If you take out the prediction, is 73.5. If you take out both of them, is 56.3. So actually, in this paper is different from that paper that is the attention is probably the most important, see. But actually what they found is the combination of them actually reduced the score significantly, right? So this is also another thing that you may need to think that I don't think you can take out distillation loss. I don't think you can take out hidden state vector loss. I don't think you can take out attention vector loss. Like this tree cannot take out. And of course you need to have the prediction, right? So finally you cannot take out anything. This is like the true story of all these papers. Yeah, in conclusion, yes. So again, this is ablation study. Yep. You can see already why ablation study is so important in papers. This is mobile bird. How many minutes I have before I turn to you? 15. Okay. Mobile bird. So I will not talk too much about this guy because this guy is not so like famous, because this guy say that, hey, this guy, the original bird, this is the configuration of the mobile bird. You have the embedding, you have linear layers, you have multi-head attention, feed forward layer, linear layer, and then you have 24 of this, right? This is the bird large. For bird base, you have 12 layers of this, right? Right? But they say that no, I will not do like tiny bird. Tiny bird just get the bird, right? And do 6 layers. I will do like this. I will restructure them so that so you can see that the embedding, the normal embedding is 1024, right? This guy changed it to 128. Yep. And also they also do some tree convolution, like convolute the embedding. So this is a rather confusing. So usually in the bird, each of the word like Chucky is flying, right? Maybe this is just like the positional plus the word embedding, right? The size is usually, I don't know, the source length, and 768, okay? This is what the original board has, right? That is, if you have 3 of them, then this is 3, right? Right, this is the original bird. But what they do is they change to 128. And you may say, why, right? Well, they just want to make it smaller, right? And then they also do some convolution. And not sure what is convolution, but if I'm not wrong, what they do is once you get, let's say this one is become, let's change to 128, right? So this guy is 128. This guy is 128. This guy is 128. So what they do is they convolute of certain window size like this, and it becomes maybe 1 number. I'm not sure. I don't know how they convolute, okay? But they do something like this, moving window, and then maybe like that. Maybe, right? Okay, but convolution looks like this. Okay, that is, you take 2 of them and then multiply with some weight, get a number, you convolute again, you get this. Probably, I guess why they want to convolute is they believe that convolution can solve the problem of the embedding being so small, probably, but we have to read the papers more carefully. But for those who don't understand what is convolution, is this. They do this 3 times, not only 1 time, 3 times. But I don't remember what are the filter size, you have to read the papers, okay? But this is the idea of convolution, right? And then they also have the hidden state size. The bird large is 1024, the bird base is 768, there is 512, right? So I don't want to talk about too much about this paper. I waste a lot of time. But anyway, the idea is they just change the structure of bird. Because they change the structure of the bird, they need to create a new teacher, right? So first they create a new teacher called IB bird large. Right, so they create a teacher of this structure, and then they create a student and then they learn from this teacher. This student cannot learn from bird. Do you know why? Because it's different structure, right? So because this guy is different structure with the bird, you need to create a teacher first. You understood? Huh? So that's why no one liked this paper, because you're trying to say that to do this way, you need to create a new teacher. No, no way I will want to create a new teacher. I just have a bird already, right? Google already trained bird for me. Why do I need to create a new teacher, right? So no one liked this paper. Okay, I'm in YouTube, right? Don't quote me that. I just want to share my personal opinion, all right? Don't put me in the drama. Okay. Yep. So you can see that when they compare with tiny bird and mobile bird, it still seems, I still think very, very similar, right? Like tiny bird and mobile bird, very similar. But anyway, I don't know what that paper, the tiny bird say they are better, mobile bird, they are better. I guess everyone can say they are better if the difference is only by 1 or 2. They can run many times to make, so it's when you guys read paper, you need to remember that. I can run many times so that I can win you. Okay, you need to remember this. So basically what I'm trying to say is that they are quite the same. And I'm not going to talk about which one is important, but again, they're trying to say that attention is very important, okay? The attention loss between the teacher and student is very important. That is what they're trying to say. But again, they are not anything new anymore. This one I can talk very quickly. It's called Mini LM by Wang in New Lips. And one more thing they add is, so we already have what? Distillation loss. We have what else loss? Attention loss, hidden state loss, and the last loss, right? The prediction loss, right? Of the student. This guy add one more. The value loss. So usually we only have attention loss, right? Attention is QKV, you get a source length, comma source length, right? But this guy also compare the value, the V. The V between the teacher and the V between the student. I think they just try and find that it works. Yeah. So they do value distillation, and they found is very important. I don't know. Seriously, I don't know. You guys can think about it. Yeah, but I don't know about this guy much. But it seems like it's better than Tiny Bird by a little bit, but not by much, like by a little bit. How many more slides I have? Oh, great. I think I'm doing well. Good. This guy is super nice. It's called grafting, okay? By the way, everything I taught you is like 2020, 2021. You may say, why you don't teach me 2023? All the 23, 22 is mostly the same idea, like same idea, but they just tweak a little bit and add a little bit. But as long as you understand the fundamental, you can read all the future papers. But anyway, this guy is very cool, okay? This guy is very cool. Listen me carefully. So if you don't follow me, you ask me right away, because I feel like this is so cool. First, you have a teacher, okay? You have a teacher. It can be a CNN or whatever, okay? LSTM, whatever, teacher. You have a student, okay? You have a student, okay? You have a student. Now, what do we do? You take one of this, by the way, the student can be smaller than the teacher, right? Right? So you take one of this layer, that is just one layer of the student, okay? Just take one layer of the student and take out one layer from the teacher. Take out, okay? Take out and replace it. You understand? You take out from the teacher and put from the student here and train one time. By the way, when I say train one time, it's not one epoch. Train and train. And then once you train, you take this one, put it here, put to the student. And then you take the second piece and do again. put it here, and but the first layer is now the teacher. You put back the teacher. First layer, teacher, you put it back, but you only train the second layer of the student inside the teacher. Do you understand my point? No. So teacher, in the beginning, you take out the first layer of the teacher. You take first layer of the student and put it here. Okay? And train. Okay? Once you train, you take out the first layer of the student and put it to the student and put back the teacher first layer, okay? And then you do the same. You take out the second layer of the teacher and take the second layer of the student and put it here and train. Do it like this until the end. And then once you get the full student, you train one more time. You train one more time. And then you get your final student model. So you may ask me, Chucky, what is the difference between this Distil bird and this guy? I think the same. But this Distil bird say that I learned from distillation, right? Right? I learn from, I look at you, how you do, I learn from you, right? This is distillation. But this guy say that no need, you just put yourself into the teacher, right? And train, and then the teacher will teach you what are the weights you must have, right? So you put you into the teacher place and then just train it. So this is a little bit the mindset change, right? And this is called grafting. Very, very interesting topic. Anyone has any? Let me entertain any questions here because I like this very much. No one likes it. I'm so sorry. Yeah. Yep. Yes.
So if a student replaces wouldn't the gap between the network also
so for example, this one is 12 and this one is 6, right? So maybe I take out the first one, I take the first one here, I take the second, maybe I take the, let's say they are 12, right? I can take the number 10 and I can put the even, I put the second one here, I can take the even, you understand? So like that. But which layer to map with which layer, again, is a problem. So we cannot answer like, so let's say I have 12 layers, right? To 1, and we have 6, 5, 4, 3, 2, 1, right? When I graph, maybe I can replace this one with this one, right? But for 2, which one should I do? Maybe you can try 3. Maybe 3 to 5. Correct? 4 to 7, maybe. But who know this is correct, right? No one knows. So the people who write this paper need to try many ways to understand which layer maps to which layer, right? And I believe in 2023 there are many theories to come how to map the layers, all right? But the key essence that I want you to understand is that this is different from this Distil bird. This Distil bird look at the final targets, right? This guy basically put yourself into the teacher, one by one. Anyone has any other questions? Okay, great. For those who don't know, like Chucky, okay, I got the idea about how to code. If you know how to take one layer out and put another layer in, you can code already. Anyone know how to extract one layer of a network? Russia say no, right? It's actually not difficult, right? You just get the right attributes. I think you can get the layers. This one is even more interesting. It's a 2022, right? It's called sparse progressive distillation. And this guy combined pruning and distillation together. So first, you create a teacher, all right? And so this is your teacher, and this is your students. Again, here, this picture, it seems like the student and the teacher same amount of layers. That is 4 layers, right? But does it matter? Does it need to be same layers? No need, right? It can be different. So if they are different, now we need to solve the mapping problem, right? But if they're the same, then we can, what this paper will do is, first, before you do anything, you prune first. Why pruning? Because we want to make the student smaller, right? So if the student exactly the same amount of layers, but if we prune, actually we already create a student, right? Like a guy that has less amount of parameters compared to the teacher. So first we prune. How to prune? Randomly, okay? Actually, I did not teach you how to prune. Actually, there are a couple of more slides, how do I prune? But let's say we randomly prune with probability of 25%. And then I graph. I take the first layer, put it into the teacher. Oh, by the way, when I put the first layer to the teacher, where does the first layer of the teacher go? Swap out, right? It swap out. And then you train, right? You train. Train with the input and output, right? Train. And then you put this guy back to the teacher, to the student, and prune again. Prune again. So you can see more holes, okay? Prune again, and randomly pick, maybe here you don't need to pick like in order. Here they put your second layer, put the teacher, and train, and then put it back, prune again, and then put the third layer, and prune again, and then train again, and then now you have the teacher, student, prune again, but next time you do 2 layers at the same time. Very, very intelligent. And then they do 3 layers together, and finally they do 4 layers together, right? But each of the step they prune, they always prune. So they prune and distill, prune and distill. So pruning reduce the number of parameters, but distill allow you to maintain the performance, right? So these 2 things fight together, giving you a very, very good model. I'm not sure you understand my point. Pruning make the parameters lower, right? But the performance drop. But distillation will balance that, because the distillation will make sure you should always answer like the teacher, right? So they will fight together to give you a very, very good model, right? So this is the final model you will get. Yep. Anyone has any questions about this? Yes. Okay. So so the Peter Rat answer is pruning is the same idea as dropout. Actually, yes. All right. So to do pruning, how do you prune? Pruning is actually very, very simple. It's just like this. The normal pruning looks like this. Let's say I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I will create something called prune mass. And I call this 1, 1, 0, 0, 0, 1, 1. Okay? Multiply together, you will get 1, 2, 0, 0, 0, 6, 0, 0. This is pruning. This is pruning. That is pruning, you just need 1 mass. And when you multiply with this mass, all the neurons is 0. So actually, because you asked, pruning has 1 problem. Distillation is much better, but pruning has 1 problem. Pruning does not improve inference speed. Also does not improve memory. Why? Because your matrix is still the same size. It does not change. So you need to understand that, a lot of people talk about pruning. You need to tell them which pruning you're doing. If you do like this, it's almost no use. Almost no use, okay? So later on, I will show you a paper, how to prune better. Actually, there's no other way to prune better. You just do what? You just cut this one. You just cut layer. That is the best way to prune. That is, instead of doing like this, you just cut. You just have this left. This will improve inference speed and also improve memory. But which layer to cut? This is also a problem, right? So a lot of research is going on, and very, very interesting. But I think I don't have time, right? You next, right? Okay, thank you very much. We have a next topic called parameter efficient tuning, right? So please welcome Khan. Thank you.
get this. Okay, test. Okay, so for now you have studied about the quantization already, but yeah, you can think that we have teacher, but the question is that why we have to cut some part of the teacher out? Like we have Shaggy, but why we have to cut his arm, his leg, something like this. So they have one idea that instead of we cut them, like his arm, his legs, can we add something more inside his body or not? This is the idea of the parameter efficiency. Okay, this is the idea. Yeah, I think you can see it there. Yeah, you just try to fine tune some part of the model instead and add. You just add something and train that one instead, and you keep freezing the entry of the model. Yeah, this is the idea of the parameter efficiency. Oh, they have another one. And another one is about the quantization. Instead, we do about the pruning because pruning does not improve any inference speed or memory, right? The idea of the quantization is like the model that you have is a 32 bits. You just try to change to be 16 or 4 or 8 bits. And it said that if you change that bits to be smaller, it can improve the memory footprint and speed. But maybe we can see each one. What is the technique of the parameter efficiency try to do, or even about the quantization? Okay, maybe we can see from the first one. For this lecture, it's not same as the prompts. Okay, because prompt is like you just add the text like a handcuff, but in this case, it's like you have to set the config inside the transformer instance. So maybe we can look at in this one called adapter, but sometimes we can call as a sequential, because if you see in this this figure, you can see that this is the one part of the transformer layer, but you can see that the yellow one is the one that we add inside. Okay, but inside of this adapter, you can see that it actually just another linear layer and linear layer, and they add the layer to the middle. So what does it happen? So instead of you try to train out of the model, you just feed multi-head, feed forward layer and layer now, and you just train only this one. Right? You just train only this or only this. And it said that if you try to train only some part of the model that you have added, it can get the accuracy same as the one that you train with the full fine tunings. So it's quite strange that why you just add some small parameter, but it can train and get the performance same as the full fine tune ones. Okay, but the problem is still be the same. Like you try to fine tune already, right? But the way that you have tried to fine tune is just only one single task. Because yeah, if you remember the last time that I had said about prompt tuning, right? They try to solve the problem that you don't have to care about the to try to fine tune many tasks. Yeah, but in this paper they still have the problem. Okay, yeah, as I said, this is the accuracy. You can see that the first one is a fine tuning. You can see that it's get the average is around 80.4. But you see these two of these kids, what is the number of this one? So you can see that previous figure, they have a feed forward, naturally just linear layer, right? And because you put the linear layer, you have the hidden state of the input, right? And you have to get them as a smaller. Between you get about the linear layer, right? You have to get another number. Sometimes we can call this number that get smaller and get back to be the same number we call as the bottleneck. Okay, so it means that this number is the value of the bottleneck. And it said that if you use about it, the bottleneck is about 6. You can get the parameter that has trained only 2%. Okay, and but the thing to average, the number that it has trained is like if you use 8, okay, or even 256. This is the best performance that they get when they try to fine tune with the adapters. Okay, and this is another one. Yeah, previously it's about the sequentials, but in this case, they try to change from the sequential to the parallel instead. You can see that now the adapter has separate from the inside the. It's actually still inside the in transformer layer, but it does not try to pass with the other norm and other feed forward, but they try to pass with the multi-head instead. And they said that in this paper, they said that if we do something like this can improve performance with tasks, multi-tasks. Okay. Yeah, it's like if you use this architecture and you train with many data set and many tasks, they said that this case it can be better than single one. Okay, but it's still drawback again, like it cannot balancing about the variant tasks much, but it can improve more than the sequence one. Is there any question? No. Did you confused about how to add this one or not? So maybe, I'm not sure. Can I go? Yeah, as I said, idea is simple. Like you have only linear layer and just lay loop, and you have another linear layer, and between you get from the input dim to get the same output, you just have a one bottlenecks, and you just add this inside the between the feed forward or between the multi-head instead. Okay, and yeah, so we can see that after they can try to with some smaller, but two of these cases still have a problem with multi-task. So we come up with another one. This is called adapter fusion. Instead of you adding only one adapter between layer norm with the sequentials or the parallel, you just try to fine tune with many tasks. Okay, and you add them as a many adapter inside. You can see that in this case they have many adapters. So we can think that the first adapter is a one single task, and second adapter is a second task. Okay, but between you put this one, they have another layer called adapter fusions. If the idea is that you have to combine all of the adapters, the linear the linear one that you had seen, and combine with another QKV. And it said that if you try to do this, you can see performance in this one. Okay, you can say that if you try to train, and you can get much more higher probability. Okay. Okay, this is another one. Now this is not an adapter. We don't have to add the configuration inside the transformer. In this case, it's called PEFT tuning. The idea of PEFT tuning is like instead of you add some parameter inside of the transformer, right? You just add the parameter outside the transformer instead. Let's say you have, I should draw some image. So let's say you have Shaki is sushi, right? And you have to put them to the embeddings. And inside of after this, you have many transformer layer in 1 and 2. This is the same. This is the same. The idea inside of the PEFT tuning is like you just add another parameter in front of the transformer instead. So idea is like you just add the initialize thing, you know, over here, over here, over here, and you just put this guy to this. So what is the thing that you can see? Now you have, initially you still feed off the entire of the transformer layer, but you just try to fine tune this one instead. And you can see that these kits, it can give much more smaller additional parameter that it has trained if we compare with the adapter ones. But the things that this one have a problem or a drawback is like when you try to fine tune this, is have to spend more time more than the adapter ones. Okay, this is the idea of the PEFT tuning. And yeah, you can see that you can see this statistic. Okay, you can see that we have to use much more the data side as well to get the performance same as the fine-tune one, or maybe be the fine-tune one. Okay, and yeah, we have the prefix tunings, and we still have another one called prompt tunings. So what is difference between prompt tuning and prefix tunings? Initially, it still be the same, but you just sorry, something. Yeah. Okay. Instead of you add the additional parameter inside of the transformer layer, right? You just change a bit something. Now you don't have to add this one anymore. You just add the additional parameter in front of the input embedding instead. So let's say you have the Shaggy is sushi, right? Instead of you put three of this word, you just try to create the random embedding instead. Random embeddings. But how much you have to create in this one? The paper has said that you can try to add one. You can see in the figure number 2, or maybe you can add like around 50, and that's, it depends on what tokens that you want to add. And you just try to put all of this inside the model. It's like you just train the data set that you have and just random embedding inside. And it said that you train only this one, you can give the performance same at the PEFT tuning. But yeah, it still be the same problem, like you need the large or the quite big model to train, because if you want to do this case, it's like you have to practice the random embedding to be much more stronger embedding. It's require the size of the model as well. Is there any question? It's not same as the previous one. Like in this case, you just try to create the random layer in front of the transformer layer. But in this case, you create the random embedding instead. So it means that if we see the previous one from the PEFT tuning, if you think about the input sequence, it can be like batch size, sequence length, and hidden dim, right? Dim. But in this case of the we wrote over here. Okay, but in this case of the prompt tuning, you have to have batch size, sequence length, and you have maybe I'll call additional embedding and hidden dim. So you can see that 2 of these cases, the prompt tuning, they add another embedding instead. So it's like you force to or create the random embedding to get much more faster, much more stronger. But yeah, when you do the inference, you just extract this one and you will get the random embeddings. Okay. And you just add some prefix that you want, like Shaggy, and you can let them generate. Okay, this is the idea of the prompt tuning. But yeah, in this case, it still do only one task. So we have another paper called prompt transfer stability. The idea is like, let's say you have the prompt tunings, let's say you train with some tasks. Is there any possibility that you use the previous one that you have trained from the prompt tuning and give to another models, and you test with a different task instead? This is the idea of the cross task transfer. Like let's say you train that prompt tuning with the sentiment analysis, but you try to change to be about a NLI, something like this. Does it improve, or is there any way that we can improve or not? And it said that, yeah, if you try to train the random embedding from the previous one and give to the new informations, yeah, it's sometimes we can give the good performance as well. Yeah, but in this case, they has tried to do with the two things like cross task transfer, or you can do on cross model as well. Do I go too fast? No? Is it? Okay. And yeah, they have another one as well called the parts prompt tuning, enable for prep learnings. What a difference in this one. You can see that from the above one is like you have some tasks, but in case that you want to do a task, you have to create one prompt tuning for one task, another prompt tuning for another task. And you just, if you want to do another task that you call a target task, you have to integrate all of this. So it's like the problem is you have to fine tune each one, right? Or the yellow one can be like sentiment analysis, blue one it can be NLIs, the third one can be question answering. Yeah, but in this paper, what is the things that they want to do is like, can we combine all of this prompt tuning to be only once, and it can conquer every task that you want. So the idea of this is like, you still have a short task, okay, and you have the embedding that come from the sentence, but the prompt tuning that you have, you try to share all of them when you try to fine tune. So you can see that this one they call a prompt decomposition. What does it mean? It's like when you have a task specific, or this is the prompt that the first prompt that you have, but you change, not change, you add another prompts that call a task share. So it's like you have in this case you have four prompts, like each specific one and share one. And instead that you train something like this, and you just give a task share that you have to another model, and you prove and you use this, and it said that the prompt that you have shared from the one that you train with the different tasks, it can give the performance same as the one that we do the standalone. So you can see that in this case, actually in this paper they have tried to compare with another PEFT, like full fine tune. Yeah, this is the normal one. And another one is adapter. You can see that it can give some performance. And yeah, they have with this and the existing approach is about the PT and SPOT. Yeah, and you can see that two of these cases just only 92%. But if you use this technique is MPT, it can give 22%. But yeah, we can see that in this is cannot be the fine tune one yet, but at least can get much more bigger performance, because in this technique they can do many tasks in one time. Is there any question? Okay. Okay, and yeah, and this is, I think this is the last one of the PEFT, okay, which is called a low-rank adapter for LLMs. I think this one is quite most popular already. Why this one has popular? If you can see that we have adapter, we have prefix tuning, we have prompt tuning already, right? But all of this, the things that Laura has tried in this experiment, in their experiment, they said that speed latency, memory footprint that has trained with the prefix tuning, prompt tuning, or adapter, all of them quite spend much about that one. So in this paper, they have, is there any way that they can reduce that memory footprint or even inference speed techniques? Oh, okay. And what is the thing that they has tried to change? Instead of you add some additional parameter inside of the transformer layer, outside from transformer layer, or even do about the random layer. They said that they just use another additional transformer layer inside cell attention instead. What does it mean? So you can see that, let's say this is the inputs, and whenever they go inside the cell attention instant, we just freeze this one. We don't have to train this, but just add this one, two of this one A and B. What does this one mean? In their paper inside, they call this one as a decomposed matrix. Okay, you can see that this one is like a one parameter, and they can change the parameter to be smaller and change it back. So that's why they call as a decomposed, because it's changed from the bigger to smaller and smaller to be bigger. Yeah, but the thing that they has initialized inside of this parameter, they said that they set the A1 to be only the, it depends on of the mean distribution, but all inside of the second one B, they change to be 0. Before we go about the statistic, maybe I'll show what does inside of the things that paper this one try to do, and why it's quite much good. So now, so this is the same figure, but I had changed somewhat some illustration a bit. Like, let's say you have cell attention, right? Cell attention. So you can see that if we try to fine tune and train them with a new one, right? You have to change all of these parameters inside. Let's say this hidden dim is like 100 hundredths, and if you change this, it means that you have to change the parameter inside is 100 multiplied with 100 is like 1,000, 100,000, right? 10,000, yeah, sorry. Yeah, this one is quite huge because you have to change one cell attention, right? Per 10,000. Let's say you have 2 layers. You have to multiply this one again, right? So this one is, actually any full fighting have this problem because you change all of the parameters inside in each layer, or in each, not inside the transformer layer, but inside the cell attentions. But in this paper, they said that, is there any way that you try to fine tune? Not full fine tune, okay, it's not full fine tune, but is there any way that you try to add additional layer, but it's just change? It's not change, it add and train with a small parameter. So in this case, in this of the LoRa, they have, let's say they have A, that one I has shown, but in this one they have D, hidden dim, but another shape is called R, okay, they call R as the ratio, okay, and they have another one matrix, it called R again, and go back to D. So you can see that if we think about this case, if we do about the calculation of the parameter that they have to change, you can see, let's say I set D is 100 against, but they set R only 2. So if you think about this one, it's just only like 100 multiplied 2 and plus with another 100 multiplied 2 from the second one. You can see that it trained only the 400 parameter instead. So you can see now like it's pretty much smaller now because you don't have to spend 10,000. You just spend only the 400 parameter to train. Okay. So initially you can calculate this in even from the prompt tunings or prefix tuning or adapter tuning, but yeah, the idea is that they calculate is something like this. But you can see that initially I draw over there already. You try to calculate the percent that they use. It's like 900, right? It's just if we no. 6. Yeah, it's like it's spend only, it's reduced 96%. Yeah, it's quite small already. Yeah, and you just instead of you train this one, you just feed this. But instead you feed, right, you have to combine this one instead. So it's like you try to train this and practice this to get much more stronger. The same idea is like, yeah, on prefix or prompt tunings, but in this case, they try to let these composition metrics to learn from the cell attention instead. So it means that these kids, it can keep much more better because they learn from the cell attention, not outside the transformer layer or not after the norm layer or feed forward layer that adapted. So we can look at back to the statistics. I'll go to the first one. Okay, maybe look at the lower one first. In this paper, if you look at insights, they has checked in many birds, GPT-2, GPT-3 insight, and trained with the many different techniques like adapters. This one is, I think this is prompt tuning, and this is a prefix tuning. Yeah, and they have another one called BitFit. BitFit just only full fine tune only the bias. Okay, and you can see that let's say we have the original parameter like 175 billions from the GPT-3, and yeah, this is the parameter of each one that they have trained. So you can see that sometimes LoRa is still quite big. They train with the 40 billions or around 40 billions or 4 billions. But if you check the accuracy from each one, you can see that if we compare for full fine tune and the things that LoRa has fine tuned, sometimes it can keep much more higher. So they said that you have trained inside just small thing inside the cell attention, but it can get good performance than the full fine tune one. Okay. Yeah, and yeah, you can compare with the adapters, so it can get much more than adapter, prefix tunings, prompt tuning as well. And what is the top one? You can see that in this case, they try to do the training and inference, and they can say that the LoRa or even the full fine tuning is spend a lot, it spend a short time from the latency. Okay, when they try to generate the outputs, you can see that the adapter, they get the number more than the one that adapter have or full fine tuning have. Is there any questions? Yeah, I think it's quite theoretical technique of it. Like we have to set and configure the cell intention inside at some parameter. Okay, maybe I'll show how does it look like for the LoRa, but maybe I'll show for the everyone. Yeah, maybe I'll show every techniques. Okay, you can see that prompt tuning just adds the random embedding in front of the embedding, right? You can see that we have another parameter called subprompts. Okay, and you just concatenate from the subprompt and X input that you had at, yeah, and you concatenate and you call this one as a new X, and this new X has changed the sequence length because it has come from the sequence length from the X and another sequence length from the subprompts. Yeah, and you can see that in this case they add 50 number 50 tokens, so it means that this sequence length should be at more 50. And okay, this one is quite difficult, but so let's say this is the layer norm, fully connected layers, cell attention. So what does these things they do inside? So instead of you use the prompt tuning, that one, you just add the prompt tuning inside this one instead, because this is the X. This is to be the X of the transformer layer, but this one does not relate to the prompt embeddings. Okay, and yeah, this is the last one of the LoRa layer. You just have the parameter inside from the cell A. Yeah, this is based on distribution of the standard deviation, but the second one is based on the zero torch. So it means that the parameter of the number B is 0. Yeah, and you just add multiply together and multiply with the X value, and you just scale of them. But whereas the position that has at them, yeah, you just let's say you have the transformer inside this one. Let's say you have a linear layer. You just add this LoRa between two of this. Yeah, but you can add inside. But maybe, yeah, this is a simple idea. You can try to do as a configuration of the cell LoRa as well, and make them as that feed forward. Okay, yeah, and they have another paper ideas like, can we combine everything like adapter, PEFT tuning, and prompt tunings? We can maybe this, yeah, in this paper they draw the figuration is quite good. Like you can see that the green one is the position that adapter has stayed, but the PEFT tuning this the position that's this one stay, but this is the position that they have stay. You can see that all of this technique they does not state the position of their technique is in the same position. They have many intuition like why they at the top or even inside of the maybe they why they at inside of the cell attention layers. Yeah, and yeah, in this paper they said that if you try to combine everything in once, and it said that sometimes it can improve the performance from the exam or even from the machine translation. But I would say that it's not always in this, like because you have add many parameters inside, and the parameter that you have spent on the fine tuning is gonna be much more. I think this one is it's not this number. It should be get more than 2 of this because they combine all of the parameter inside. Yeah, and this is another one called quantizations. Yeah, the techniques of the quantization is like instead of you use all the full model, when you do inference or full fine tuning, you just change the bit memory footprint inside. Okay, so yeah, they have another paper called LLM in Edge from team the paper. There's like you just want to do reduce memory, which is it can reduce the computational costs. But the thing that they has tried to do is like you just change the representation from the weight, or even do the activations with the lower precision. Yeah, as I said, you change 16 bits to be 8 bit or 4 bits. Yeah, but in this paper they said that they try to use 8 bit instead. I will not talk about this technique much. I'm still not expert yet, but like let's say you have X. This is the parameter inside of the text, right? And you have a weight from the one that you had trained before, maybe the pre-trained one. Yeah, basically inside of the Huggingface or the model that you had trained from the PyTorch, right? They always try to use, even I'm not wrong, it's 32 bits. But in this case, you have tried to change to 15. No, 16, and that's it. The first idea that you do. But in this paper, they said that instead of you use 16, you just use 8. Yeah, and they said that it can keep a performance same as the 16 or 32 as well. And yeah, they have another one called QLoRa. Instead of you just use LoRa, you just add quantization of the LoRa as well. Yeah, in this case, you can see, let's say we have full fine tuning, and you have, let's say you have a base model from the 16 bits. When you try to optimize, they optimize with the 32 bits. But yeah, if you have even you use the LoRa, you still use the 32 bits inside. But yeah, but what is the thing that QLoRa they has tried to do? That's before you try to fine tune with the LoRa's, you has changed the model and you compress them to be much smaller memory footprint to be only. I think this is the normal 4 bits, and you just try to fine tune that one with the LoRa, I guess. But the things that this technique have add more is like instead you do a quantization to get a more smaller bits, but they get double quantization inside. Like let's say you have this is the weight, right? In that inside of this thing, we do a dequantization. So what does it mean? Yeah, we have to look at this. So let's say you have a weight inside, and you have a constant that you want to change from the the bigger bits to be the smaller bit. You have the first dequantization from the first time, and you add another dequantize. So it's mean you double quantize them, and you can give in this you can give another weight parameter inside that much more change the memory footprint, and you add back to that weight, and you try to train with this one. Yeah, and yeah, they have that technique called double quantization. And the first one that I say is the 4-bit normalization. They just train the main model to be much smaller. And another one is called pace optimizer management memory spike. What does it mean? Instant, yeah, we always have a problem like when we have a smaller GPU, right? And the model is quite big. When we try to train them, yeah, at first we can train, but it's like when they keep more memory footprint from the GPU, it can get out of the memory, right? So in this technique, it has come from the NVIDIA. What is the things that they has tried inside? It's like if the CUDA that you have inside had exceeds and is out of the memory, this technique, I think this one is we cannot do this, but the idea is like they just change the GPU to CPU instead. But when GPU has available, they're gonna put the things that GPU contain back to the things that from the GPU back to GPU instead. So it's like it can fix the problem that we get the out of memory. Yeah, this is the technique that's QRA has to. Okay, yeah, and this is a summary. Yeah, we have the adapter, prefix tuning, and prompt tuning. Sometimes we can call this one as adaptive because they adapt and add more parameter inside because you add some configuration, right? But LoRa initially does not. Initially, it adds some parameter inside, but the thing that they do like a scaling because we can see that from the figure that has drawn, it's like we don't have to add small parameter that you do a full fine tune with the 10,000, but you just add some decomposition metrics and get only 400 instead. So it's like you scale the things that they learn. Okay, and they have another interesting paper as well. Initially, I does not much more explore yet, but it's called mixture of expert. Okay, what it does, this one try to do instead of you add additional of the adapter prefix tunings, LoRa. In this case, you just try to add many feed forward after you get after you put the cell attention instead. And it said that if you have many feed forward inside, and you try to fine tune with one task, and you group and combine this feed forward, it said that it can expert in many tasks in one time. Yeah, but the idea is like you just have many feed forward instead of the additional parameter that you add in different locations. Yes. Yeah, and yeah, you can see now we have Aurora, right? But Aurora does not try to do about the multi-task yet. Yeah, they have mixtures of LoRa as well. And I think they have another one called LoRa Plus. I think it has public 2 or 3 days ago. The idea is like, yeah, I did delete, yes. But the idea is like, when you try to fine tune the LoRa, right, the things that LoRa has a problem is like, they use the same learning rates. What is the thing that they try to solve is like, we have A and B, right? We just train 2 of these with the different learning rate. And it said that if you use 2 of the different learning rate, it can give much more speed when they do the inference. Yeah, that's it.